see the major features here. Firstly, this kind of depression area over here is the Johannesburg granite dome. And that has been pretty fundamental in updoming younger rock formations and exposing the important gold-bearing reefs, for example. And we'll talk more about that later. And then just to the south, this high area. Okay, so coming back to this, this here, known as the Witwatersrand Plateau, is the outcrop of the Witwatersrand, main gold and main gold-bearing reefs of the Witwatersrand Basin, which we'll talk about it later. Just for comparison, and this talk is kind of aimed at not necessarily professional geologists, but at in general for tourism, etc. So if you compare this, you can see very clearly where the Witwatersrand rocks are in yellow, and the granitic rocks there in pink. And then here to the south, you can see this circular structure over there. That is a beautiful dome. And in the center is the granite again. And then you can see the Witwatersrand strata in yellow pop up again because they've been updomed and beautiful. But the reason for these domes is completely different. So we'll talk about that later. And then to the north, you'll notice a very clear topographic feature there. That is the Mechanicsburg fault site. For reference, the dam is situated there on a fault block. And then there's the fault. So hopefully the fault doesn't move through. And then to the south, you get another range here. That's called the Dustberg. And then to the south of that, another range, and that's called the Pine Ball Hill. And that whole area is known as the Bunkenveld. And the Bunkenveld means valley and ridge terrain, or crested topography. And then north of that, you'll notice this is a low-lying area, the greenish color. Those are the mafic rocks of the Bushveld complex, with the important layers of chromite, platinum, and then vanadium bearing magnetite at the top. So you can see that the topography reflects really clearly the geology. This just shows again the reasons for the two domes, the updoming of sediments over here due to meteorite impact, and the updoming here of the Johannesburg dome due to normal tectonic processes. Now the Witwatersrand edge is right here, and there's the botanical garden sitting right on the edge there, where the contact between the lowermost Witwatersrand strata lying on the basement of Greenstone and granite. So it puts in perspective the present erosion surface is obviously there, but previously it might have looked something like that before erosion took place. The other important feature to notice here, this looks like a geological map, but in actual fact it's a vegetation map. So again, it is pretty clear that the vegetation is reflecting the geology. For example, this is the Igoli granite grassland over here, and that's why it is there. That's what it used to be like. It's now largely developed with urbanization, etc. And then various other things which you won't go into. It's just to illustrate the amazing correlation between geology and vegetation types. This just shows the situation with the upgrading now. I've explained what that was about. Here you can see again the original situation, and then with the upgrading, the tilting of the strata, and exposure of the gold-bearing reefs, and exposure of the bushveld complex over here. So and sagging due to the weight of the bushveld complex. So very, very important that structure in this whole area. So now, what the garden have done very successfully is collected or had samples collected which are numbered. Now, the numbers that you see here are the same that you will see in the garden. So number 1 is the granite, I think it's actually from the beautiful dome, where it's a granite. So very similar to the granite over here. And then number 2, 3, 4, and 5 are all greenstones, and you can see the greenstone belt over here. In fact, we're sitting on ancient greenstone right here. And then samples of the Vijoen, which we'll look at, samples of the quartzite, and in particular the magnetic shale, which played a very important part in the tracing of the conglomerate reefs. And then on to the Pebbles lavas, which actually entombed the Vijoen. They occurred to the south of Johannesburg, dipping away again to the dome. After the Pebbles, the dolomites of the Transvaal group, and you can see clearly this bluish color here. And then onto the Bunkenveld with the Timeball Hill, Dustwood, and the Pebblesburg, and samples of these. And then onto the Bushveld with samples of the Bushveld, illustrating the Blackberry rocks and so on. So you can see a pretty nice comprehensive traverse, if you like, to the area. And then with a couple of outliers, the Pilansberg over here, and then the Hereford area over here. So that gives you an idea of what the rocks are as well. Follow that pattern. Okay? And those numbers, as I say, correlate with the rock numbers. And this eventually will be put into a brochure to explain. And that's the time column. You can't see it well, but from about 3.6 billion years old over here, which is a very ancient, we believe, a very mafic crust. In other words, not much granite around. But then the major influx of granite from about 3.3, 3.4 over here, and then the Vijoen and the Pebbles, and then up into the Bushveld, the Palabora complex also comes into it, about that age, Bushveld age, which is just over 2 billion years, and then up into the first signs of multicellular life, about 600 million, etc. And then up into all the recent stuff, which is the advent of, well, firstly, human beings at about, well, human-like creatures came in at about 3 million years ago, occurred in the cradle here in the Dolomite, and there's a sample of cave ledger over there. It's a pretty good representative cross-section of geology, and it means a lot more. Once you've seen the sample, then this talk, which means a lot more to people unacquainted with the geology. So that's the layout of the garden then with the numbers. You can see they go right to go through. We start over here, one over through, that over here. So I'll just read those. So in the beginning, a very fiery start to this planet, the eruption of virtually total melting at the mantle took place, forming a very unstable hot crust. And the volcanics that poured out were very unusual as well. And these are called commodites. And they occur, or they were described in the Commodity River Valley, in the Barberton Belt, and hence the name. But the characteristic of them is that they're the hottest rocks ever to have extruded onto Earth's surface, 1600 degrees centigrade. And it's called spinifex after a spiky Australian glass. Then on to this, the outcrop of Martiart here on in the property. I give that sample number 2. And the important thing is that when you erupt lava into an ocean or an aqueous body, it tends to form, and those are some of the pillow structures that I'm talking about, occurring in these ancient belts of old crust called Greenstone now, pillow lava, so on. Are these sediments? The first mural words you have here on the right, pillow lava, well developed, and then you have shear commoditic lava over here, and in between we have this very dark band, which is called a chert, and that band contains the oldest forms of life yet identified. They occur in these biomass, as they're called, and are being intensively investigated at the moment. These are the biomass. You can see the darker layers here being disturbed by sedimentation. You can see how disturbed later sediment coming in. All part of the sequence of volcanoclastic rocks. You can see some dark bands from here and from here. Those are the biomass that are creating a lot of interest at the moment, and all sorts of research papers are being produced. 30 forms of life in Barberton, both in the lower sequence of volcanics and also the upper sequence of sediments called the moody sediments. And there are big drilling projects on the go, drilling specifically to look for primitive life. And the rover, Mars rover, the only real justification for the Mars rover is to find life on Mars, probably. And what they're looking for, biomass at about 2.4 billion years old. When Mars, and the thing is being preserved there, and they're looking for signs of water, which you can find from things like ripple marks and so on, and where there are any organic material associated with that, there could be life similar to what we find in the old rocks of Barberton. So NASA has put a lot of effort into investigating rocks in these greenstone belts of these spherules, which are the result of meteorite impact. So at that time, the Earth was being bombarded by meteorites in profusion, and they divided the Earth, and that material was preserved in spherular layers. So there are all sorts of interesting things to be found. And that's just a depiction of what the Earth might have looked like in those early times. So we've got meteor approaching the Earth, impacts, we've got volcanic eruptions here, we've got algal materials here, maybe some meteorites, spinifex textured lavas, etc. So it was a really unfriendly looking place. It was an ozone type atmosphere, no oxygen around at that time. Okay, so that's just the basic. We can now have a look at the brightest one. We're looking at the basement. We look firstly at the granites. Various granites, 3.4 to 3 billion years, formation of the first continents. Just a depiction of how these granites formed. We've got the granite expert here. I hope you concur, Lawrence. So here we have these early bathytes that we like coming up, invading the early crust, which is that Mardiite dominated material, incorporating zeolites, and then the Greenstone belt formed over here. The Botanical Gardens are sitting in a position somewhere like that if we want to. And this is what it looks like when the granite intrudes into the early crust of the Earth. That's in Barberton, called the living Meteorite, with the granite there, etc. Then it's slightly younger, and that's the granite that you'll see here in the gardens. It contains xenoliths of the early crustal material. That just shows the granite intruding into the greenstones again, with two generations of granite giving different textures, different colors, and reworking of those granites causes granite being a product of the partial melting of those greenstone levels. And that's what the granite outcrops look like often. That's a really good example Alice had in Zimbabwe of one of these granite domes. They form these characteristic domes from these granites, forming these old continental nuclei in Africa and the other continents as well. So we have a look at the granite, which is that one there, and then the Botanical, 2.7 to 2.8 billion years. So here we have the Botanical, which I explained, You'll just have a look quickly at some of the rocks there. That's why it's exposed, because the granite pushed it up. If that granite dome had not been there, we might never have found the deposit, or it might never have developed. You know, it's quite important. That's Orange Grove quartzite at where we're sitting right here. That's the Vijoen waterfall. You can see there some shale material over here and shale over here, and making a perfect nesting place. I think right there is where the black eagles nest. So this area, this place is really famous for the black eagles, and the bird life is tremendous. I think Alice mentioned a number of about 240 bird species as well. So the type of geology of birds. And where the people are walking here, it's all greenstone, weathered greenstone. So you can see how the hard quartzite forms that resistant ridge. And it's important that on that resistant ridge was where Fred and Harry well, just behind us here, a few kilometers south, in quartz vein. And the quartz vein that they discovered it looks something like that. You can see there on the left. And that's Wilson Gold, which is close by. That's the old working of the Confidence Reef of Stephen Brothers. However, that was not the answer. And it took a little while before they realized that the real bonanza lay not in vein quartz, which was the main carrier of gold in all the gold fields at that time, in California, in Indigo, in Ballarat, all over the world. So people just looked at quartz veins, but they didn't really take too much notice of pebbles. And this is the outcrop of one of the two important gold-bearing reefs. The main reef over here, quite wide over here, with conglomerate and sandy layer, another sandy layer, and then the main reef leader, which is quite narrow. But it occurs continuously over at least 12. And that's how these conglomerates were deposited. In sort of delta-like clumps over here, you can see the various conglomerate layers. So here's the main reef group, the Kimberley reefs, and higher reefs over here, and the Montreal conglomerate at the top. You can also see there's the Orange Grove quartzite at the bottom. It was deposited in just offshore or in a deltaic kind of thing, or either part of the fluvial system that you can see over here. That's what it looks like. Quartz vein, quartz pebbles mainly, but also these black smoky quartz pebbles. But importantly, in the matrix, quite a bit of that shiny stuff, which is pyrite and gold. So that's the stuff that's mined. And there's some very good examples in the garden of this. You can see this is sandy material. There's the base of the channel, there's pebbles. And there's the upper part of the channel with more conglomerate over here. And right at the top, some very nice gold values. So that whole thing there constitutes what's called a reef. And this is one of the Ellsberg reefs in the West Grand area. Gold is associated with carbon like this. And that reef there is called a carbon leader. And one of the richest reefs of gold in the entire Vijoen basin. That reef may be only a couple of centimeters wide, but they've sunk shafts down to 2 kilometers to chase just that. So it's extremely rich in gold. So the question is, what is the association of carbon and gold? And the answer lies in the fact that we believe that the carbon was produced by living organisms again, that live in the environment of the Vijoen, and they deposited gold, which might have been in solution, coming into the basin and attracted the gold and uranium for that matter as well. So, in other words, life was quite important in forming concentration of various minerals, and particularly this gold in the Vijoen. But that's a big story. That's just the idea of how things look, showing the rivers, showing the channel, showing a more continuous reef over here, showing these kind of algal mats, which gave rise to carbon leader, etc. So one can reconstruct more or less what it looked like. And then from early beginnings, the Botanical goldfield is now absolutely huge. So we're sitting just over here at the Botanical Garden, and from here, the whole area expanded tremendously. One thing I didn't mention is that in the lower Botanical, you get magnetic shales. There's very samples of magnetic shales in the garden here. And that magnetic property was used to trace the magnetic shales under young cover rock just to the west of us here, towards Randfontein, and then eventually under cover to form the Pebbles goldfield. Okay, so then fiery end to the virus rock, and it was covered, the pebble layers were covered by outflowing lava, huge outflowings of lava here, and you can see the pebble beds over here, some of the algal material over here, and this lava effectively sealed off the gold-bearing leaves forever until they were re-exposed by the tilting of the Johannesburg gold. So that principle of lava was important in that it's kind of entombed with the virus rock. And it's a good example of a fundamental principle in geology called uniformitarianism, which means the present is the key. So if one sees pillar lavas forming off the line, you can actually see them forming in this environment here, which is called the central contact for obvious there. And we know there must be pillars because we can see pillars just like this forming today. So that principle is really important. It's a good example of how it works. There's the chemical lava, and in lava, you can see the gas, the light trails of gas cavity. Okay, then let's then ocean oxidation event in the dolomites and the algal stromatolites. Okay, so we'll point to there. And these are some examples of the algal stromatolites, very well displayed in various parts of the dolomite formation. This is here dolomite on chip bands. These are algal domes of these stromatolites. I think those are actually in the garden. There's some beautiful examples in the garden of stromatolites. And there's the normal dolomite over there, there's the chip band over there. And when you weather the surface, that's what they look like from the top, little domes, called algal domes. So the present is the key to the past. What you're looking at here is Shark Bay in Western Australia, where they have living stromatolite colonies. So very interesting comparing these things to these very old ones over here. But the important thing is that through photosynthesis, oxygen was liberated mainly into the ocean at that time. So it's a major oxygenation event, and these stromatolites are pretty important in that regard. And that's what they look like. Now, the other important thing is that over here, the oxygenation caused precipitation of iron and manganese. To the extent that our major iron ore deposits are occur just above the dolomite, where there was still oxygen around, and you got oxidation of the iron at that time, and get some of the world's huge. So that we needed oxygen to oxidize that iron. Okay, 2.5, 2.2, talk about gallium-rich landscape of the bunking cell, and I explained that earlier on, the method does work, my honeys and kind of real range. Now, it's interesting that the first quartzite in the bunking cell, which occurs just above the dolomite, is very iron-rich. You can see there, that's an iron-rich quartzite. And there's a beautiful example in the garden of this iron-rich quartzite. So it forms the first band of the bunking cell, dark most of the quartzite there, and that's built of that iron. And then just further on in the bunking cell, you can see in the distance there the Dustworth Range. This is called the Wood Valley. On this side here, the Holliesburg with a cable way out to the top of the Holliesburg. So then that's just the Johannesburg showing some of the important features. This is the stepping down towards the right, and these are the native rocks of the bushveld over here. You can see very beautifully this is what's called a graben, down folded rock, one fold from here, another fold from here, and this rock has been down thrown and interrupts the continuity of that range. So there is what's called the scarp slope, and on the other side called the dip slope. So that's a typical bump control situation with the ridge in the valley and then another ridge. And again, evidence of how the rock is the ripple marks in the polypid quartzite. I give you examples of that in the garden here. 2.0 final placement of the bushveld complex. That's a big story, but so the bushveld complex had their different ideas. Essentially, the eastern well, the first event here was the sediment of the floor rocks in the Johannesburg, forming the floor, and then there was a huge. Now this was a bit controversial. A huge acid lava episode during the Rooiberg fault site, which is that color there. They called rocks there, but they're actually huge rocks. Okay, so then the first replacement was the green, which is the native rocks of the bushveld, called the Rustenburg. That's the uptop of the western one. Here is the uptop of the eastern one, which I showed you. And then here is here, you mean the granites over here, sheet of granite, and the eastern one. So that's, and then the huge rocks have been pushed up by the emplacement of both the bushveld, native rocks, and the granite. So that's a simplistic sort of model of the bushveld. The satellite imagery is particularly revealing about the bushveld. Okay, so now we can see a whole lot of things. First, we put in perspective. There is the Johannesburg granite. You can see the right color of the Pebbles colored soil. Botanical garden is right here at the source of the capital. You can then see the bump of rocks, not all the real quartzite, industrial quartzite, and then quartzite. Yeah, near the obvious to there, right on that fault line that I showed you. And then into this sequence loose rocks. Those are the native rocks of bushveld. Bushveld also divided up into a number of zones, platinum and chrome reefs, further at the base, towards the top, you get Canadian concentration in magnetite. You can actually see the darker tone there, that's the upper zone of the bushveld complex. And then into the granite, get on the coming right away through over there. And now they've got a really good collection of samples of bushveld here. So it's a layered complex. Those are just the platinum mines and the chrome mines, major mines. Now, it's called the layered complex, and you can see why. These are the layers of the intercomplex, consisting of a variety of rock types. Not a few of which are down the garden. So here we get a peroxide, which is kind of a dark color. And then we get a chrome seam over here, which is a pretty dark color over there. Then we get a more specific rock, laurite. Yeah, that spotted laurite, like that. Then we get another pretty substantial chrome seam. Then we get a peroxide overlying that chrome seam over there. Then upper laurite over here. So you'll have a look at all these rocks in the garden, and that's the UT2 come up. It's an incredible concept of chrome, but also platinum. Becoming one of the major sources of platinum now, together with the WSNBG. So that's a very important layer. Now we've got the samples of chromite in the garden as well. That's the view over there, the upper complex there, up the platinum value, up to nearly 20 grams a ton for this base. So that's big over there. That should be mined over many kilometers. And we've got a really distinctive rock called a synthetic peroxide pectoid, was pectoidal peroxide. So you can see the coarse grain nature, and you can back into a normal pyroxene peroxenite without feldspar. Again, it shows the type of layering that you get associated with these mineral layers. And then the Merensky Reef, and they've got a beautiful example of the Merensky Reef in the gardens here. Again, put it in perspective, you get what's called morite. You've got that spotted morite. Then you get a reconstituted mottled mottled morite. And then you get a little chrome seam over there. And then there's the Merensky Reef, which is a pegmatoidal rock, coarse grain. And then upper chromite seam over there. And then you've got peroxenite in the hanging wall. But just look at the values here. They go up to maybe 15 grams a ton. So it's quite narrow, but in places it gets really wide as well. But you'll see a section in the gardens where the surface has been polished. So you see everything I've explained in there. This shows you where the platinum is. And then right at the top, you get magnetite seams, which are rich in iron, titanium, and vanadium, Calabora complex, which is like a volcanic pipe, but it's enriched in parts in phosphate and in copper. So it's a very interesting occurrence. That happened about 2.049. Okay, then at about 2.023, we had a huge meteorite hit the planet. So this then, when it hit, it caused a catastrophe. It actually caused the updowing of the strata and the melting of the rock and the formation of all sorts of breccias and intrusive veinments. So, and it's given rise to this circular feature that you saw, which fortuitously, because there's been no further tectonic activity really, has been preserved for 2 billion years. So it's 2 billion years old when this thing hit the Earth. And I've explained that before, how the updating occurred. It's called the rebound, central rebound of the crater impact. And that's the crater. It is phenomenal. They call it a crater, but that's really the center of the dome, the dome center. These are actually the data from strata. Lo and behold, actually there's an old gold field here. So there's gold from it here. So it's still mine. I'm not sure if that's in the right now. Might be interesting to have a further look at those conglomerates. And then these are the outer rocks, filled with lava, and then dolomites further up. So it's a beautiful story of how you updome those sediments due to this impact. And this is what happened to the rocks. They're forming of these cones of percussion or shatter cones where the rock is completely fractured and you get this type of pattern developed in the rock. And the next thing we look at is the water bird, which is a real oxidation event. Okay, so these are called red beds. And this is the western flank of the Waterberg Plateau. And those rocks are red because the iron that was present at the time was oxygenated. So there was oxygen in the atmosphere in pretty large amounts. So this is when oxygen really became abundant, actually in the atmosphere, not just in the ocean, but in the atmosphere, and caused these so-called red beds. And they're about 1.8 billion years old. Quite a major oxygenation event. Now, those are some of the red beds that you see in that cutting with some secondary alteration like a color here in the dark. So that's where it comes from, and it's a result of the oxygenation event. Next, 1.2 eruption of the Viljoen volcano. Okay, so I'll explain briefly the Viljoen. It formed an amazing topographic feature over there. Now again, these go down over here, the wetlands, and the Viljoen pattern through the south. It's actually a volcanic pipe. And this is what it looked like. A major volcano of an unusual composition. Now the closest analogy is a volcano called Namdar in Tanzania. imagine that volcano being eroded down to the root zone of a volcano that looks something like that, producing some very unusual lava, rich in sodium, potassium, and a bunch of other stuff, minerals, including fluorine and the mineral fluorite. And they've got a very nice sample of fluorite here from the Viljoen in the garden as well. So that's the roots of this volcano. These are subvolcanic rocks. In other words, they're very coarse grained, but there's still remnants of the lava left behind that you can see. There's the fault, etc. But that's essentially the ocean. Incidentally, that is Sun City right there. The Sun City is right in one of these rings on a green foyer. Okay, so they're the rings and the different rock types. Now, they've got most of these rock types here in the garden. So you can see the outer white cyanide, outer white foyer, the green foyer, green over here, central foyer, and red cyanide, and a white cyanide, little right there. There's the Monkey Dam, which is pretty close to the center of the volcano. And the center of the Pionsberg had put up a whole bunch of signs. They indicated here. Those numbers are the numbers of rocks. You can stop there and see what the rock looks like in the Pionsberg. So again, if you get bored of looking at animals, we can't find them. You can look at rocks there as well. That's our form at depth now, with the top eroded off. Various stages of formation. Again, many of the volcanic rocks in the top one there have been removed, these rings of intrusive rock at the base. And there's some examples in the Pionsberg, red cyanide and the black rock. That's one of the rocks, the cyanide died from the Pionsberg in polish. This is the crystal with feldspar. 300 billion, okay. Huge ice sheets then covered this great southern continent, Gondwana, and including virtually the whole of southern Africa. And that's the extent of this ice sheet. You can see the whole of southern Africa is there, and you can see movement directions of the glaciers and the ice. The whole of Antarctica is covered. So that's what the ice sheet. This is a beautiful mini example of the Gondwana ice sheet. It's actually in Iceland. What you see here is an extensive body of ice. And from it, you get what are called valley glaciers. You see the glacier moving out along the valley. And as the ice melts, so the glacier retreats the whole ice sheet from these glacial valleys. But the important thing I want to point out, if you look over here, you can see some very dark material in the ice. Okay, that is the material that the ice is actually frozen and it's actually holding it and in the ice. When the ice melts, can you see what happens? See that glacier there? That fall. That's called glacial debris or tillite. And you can see it in all these glaciers that are retreating. You can see it tillite down there, you can see some tillite there. And we believe that this glacial or ice age on Gondwana land at 300 million years ago, something like this, the melting of the ice left behind a tillite. It's called a white tillite. And the other telltale sign is that when the glacier moves over the floor, the particles that are embedded in the glacier form these scour marks on the underlying material. So it's both scours, but it also plucks. So you can actually see pluck marks. The pluck marks where rocks have been incorporated into the glacier as it moves over. And you can also tell the direction of the movement of the glacier. So also you can read the rocks. Now these rocks like this occur in many parts of South Africa, like the North Pebbles. So they are very important. As I say, it helps you get an understanding of how the ice moves those times. And this is the tillite here in the gardens, which again, what you see are fragments of variable size of put up in this grey matrix material over here. That's a typical pillite. I think that's from the tell somewhere. Forest flourished after melting the ice sheet. And that's exactly what happened. All evidence here of the ice. Here is a glacial pillite moraine. Here you can see the striations in the bedrock earlier. And here you can see the growth of this forest. And the vegetation here is called Prosopis. And that vegetation, when it rotted, particularly in swampy areas, it gave rise to our coal deposits. And these are where coal deposits are formed for various reasons. You've got preservation of the leaves of this Prosopis, and they're beautifully preserved in many areas. And that's just an example of that. I think that's from the work of Rose Rose. Just some examples of Prosopis. And then, of course, coal seed. That's the product of this vegetation. 280 to 200 million, the rise of amphibians, reptiles, and mammal-like reptiles. So, just go through this. They occurred in the, I should have mentioned earlier, in the Beaufort series of the Peru. I won't go back now, but the map showed the distribution of the Brichytillite, and above the Brichytillite is the Eka, which contains the coal, and above that is the Beaufort, which contains the mammal-like reptile fossils. So this is the typical Beaufort type of you get channels of white with sandstone, and you get muddy material in the preservation of these channels of animals. And these are just some examples of Obsidian fossils from the Beaufort, a pictorial thing of the animals that lived at that particular time over there. And that is done for the Oppenheimer family. And then the age of dinosaurs towards the top. Dinosaurs started coming in, and so did mammals. True mammals, not mammal-like mammals. And that's an example of one of these little creatures, mammal-like reptile. And that's an early dinosaur over there, base there as well. And you have the first mammal over here, this little creature over here. Okay, and then as the climate changed from glacier to rivers to forest to whatever, eventually it became dry and it turned into a desert. So, and that's manifested here in a formation which is found in the Golden Gate and other areas called the cave sandstone. And you can see why it's called the cave sandstone, because of the weather. So this is more or less the end of all the animal life. And it was terminated by a major volcanic episode at about 1.883 million years. And this gave rise to this sort of entombed, if you like, the whole of Peru, and gave rise to the Drakensberg range, top of the Drakensberg, all part of this volcanic episode. And that's all the top there are the volcanic rocks, lava flows essentially, and then down here you see the white cliffs. Those are still the white cliffs of the parents, signify that it was a desert, or things turned to desert by that time. And the Guerra waterfall pouring over the edge of these basalt flows in the Drakensberg. And then the Peru dolerites, which occur at a late stage intrusions. But the interesting thing here is how they weather. That's a typical scene from the Valley of Desolation. But what happens, and this you see beautifully in the Kruger Park, dolerite dark material into previous material. And that signifies that things are moving apart. And it actually is the first clue to the opening up of Gondwana. That's when the continent started drifting. At the time of this volcanic episode and the intrusion of the magma into spaces formed when splitting took place. photographs, and you can see that beautifully over here. Kimberlites are very important, and there's an example here in the garden as well. They came in at various ages. Some of the oldest kimberlites were colored white. That's over 1 billion years old. Whereas some of the later ones are about 20 million, etc. But so the diamonds were brought up in that kimberlite magma, and as it exploded, it scattered diamonds, if you were lucky, and that sometimes they're still preserved, but other times they're not. So the diamonds were plentiful, scattered both by the eruption and still within the kimberlite pipe. And that's the kimberlite hysteria over there. But then it's very interesting that you get a whole stage of, there's the roots of the kimberlite pipe. It's now a big hole in Kimberley, a very good museum over there. But what I want to show you here is all the payable kimberlites, or diamond-bearing kimberlites, are shown in purple. Alluvial kimberlites in the rivers are shown in green. So diamonds along the Vaal Orange River system, eventually the Orange River over here, all the red dots are working. And then, if you look at those red dots, that's not the Orange River, there's the Orange River there. So the Orange River, in previous times, actually flowed and out of the sea somewhere here. But then there was river capture, and it eventually flowed into the river again over there. So the diamonds picked up again in that part of the river. And then eventually they hit the shore, and we got diamonds along the shore over here. But you also get marine diamonds going to the sea. So all these diamonds from those fertile kimberlite pipes are trapped by alluvial processes that wave action, etc. And that's one of the mines in the Orange River. There's one of these storm beach terraces with many of the minerals that go with the diamonds, such as agates and so on, that found in those storm beaches. And of course, diamonds as well. And that's what the mining operation along the coast looks like. Extensive mining of diamonds here north of Oranje, essentially. Okay, so from diamonds, we turn to some of the younger stuff, only 5 million years old. The fossils that are found in the rivers that drain from the west coast. They over there, this old phosphate mine, now I've become a major fossil crop, called the West Coast fossil crop. And those fossils are about 5 million years old. But life again thrive along those rivers, river-beaten kind of environment. And some of the animals that lived at that time as well, there was some strange looking crossing between giraffe and Pebbles, etc. This comes from the fossil record in that area. Okay, then you get on to the younger stuff, 1.5. So this is the first appearance of human-like beings, if you like. It's called the hominins. So they're preserved right here, next to us in the cradle of humankind. There's microphone stuff over there. Also in a cave in Dolomites over there in the northern, and then also down here in the front plateau. And at Taomi, that the first, and they're preserved in cave breccia. So we've got cave breccia here in the garden as well. So you can see the whole story there. And that's how the cave breccia formed. We're going to detail it. You can see the stalactites at the top of the cave and stalagmites at the bottom. You can see an opening in the bottom picture there where animals and humans either climbed in or fell in, and they're there, and they fell in, and they were preserved in the calcium carbonate environment over here, and in the breccia in the cave. And these caves are just popping up all over the show here in the cradle of humankind. That's the founder of this thing, of Roman dot. But this little skull here, which I think is a child, these are some of the skulls that they're now finding from about far back as 3 million years to about 1.3. But then another story starts developing. There's this little fix and very complete skeleton moving. Okay, so finally to the wave platforms at about 300 to 200,000 years, development of, well, and their innovation. So these are some of the caves on the south coast of South Africa. This is the Pinnacle Point cave, and in it, well, these caves here, you can see that we etched out in this case by the sea, the fault zone, the bedding plain, and so on. And in it, developed this cave bed here, because in the cave, the ideal place for humans to live. And so they left their remains and artifacts, which became cave bed here, which are actually excavating at the moment. So it's a big new game looking for human fossils along the south coast of Africa. And that's a view of Pinnacle Point. That is a few 100,000 years ago when the shoreline was about 30 kilometers out to sea. So the sea level is fluctuating, and that depends on climate change, and that depends on the melting of the ice sheet. So there's a big story to be had here in reading the sea level changes and past climates, and the development of human beings in that context. And so these are some of the innovations here. This is one of the first ones giving a proof problem for reasoning, this sort of serrated kind of pattern over here. And then this famous seal scapula, which was discovered by Thomas Bay. And then more recently, the Khoisan people, very active, very innovative. With what they've done, you might have seen them, they built what are called fish traps. So that wall over there, built with stone, at high tide, the sea comes over, brings the fish. Okay, so the fish are in this pond over there. And as the tide goes out, it filters through the rock, and it leaves the fish stranded in the pond. So those are called the fish traps for the Khoisan. So that's and then after Khoisan, I guess modern history, so we know what happened. So that's the story of